Hello all students and welcome to another video of this chapter short circuit analysis. In the previous chapter we have covered majority of topics related to symmetrical fault analysis. Basically that was a three-phase fault in which the behavior of all the three phases is same. And now we will be moving towards asymmetrical fault analysis. But before we move towards asymmetrical fault analysis, we need to understand the concept of symmetrical components and sequence networks. So our topic for today is symmetrical components and sequence networks. Basically what we already discussed, that if we have a balanced fault, then the behavior of all the three phases in case of fault is same. That is, in case of a balanced fault, the behavior of phase A, B and C, or if you are considering red, yellow or blue, all have the same voltages and current. That is why it is called a balanced fault or symmetrical. But in case of asymmetrical faults or unbalanced faults as we call them, this is not the case. In a line to ground fault, the behavior of one phase will be different as compared to the behavior of two phases. Same is the case for line to line fault. One phase is sort of normal and the other two phases are subjective to fault. Line to ground is also the same. So here we need to find a method by which we can analyze these faults. We need to convert this unbalanced set of phasors into a balanced set, because we know that voltage and current in AC systems are both in phases. So what we are trying to find is a method by which we can convert an unbalanced set of phasors into a balanced set of phasors, so that we can analyze just one phase and predict the behavior of all the remaining phases. And this is where a Fortescue theorem comes into play. Fortescue theorem, right? Now what Fortescue theorem says, it says that if you have n unbalanced vectors, let's say that we have a vector x1, then we have x2, then we have x3, and all of these are unbalanced and up to xn. Now Fortescue theorem says that in order to analyze these vectors, you can convert them into a sum of n balanced vectors. What Fortescue theorem says, that is, unbalanced set of n phasors or n vectors can be resolved into n sets of balanced phasors, and each set is called a symmetrical component of unbalanced phasors. This means that if we have n sets here, so first we will be having the first set, and within this set I am talking x1, 1, x2, 1, and all the components within this set will be balanced up to xn1. Similarly, sum x1 part 2, x2 part 2, and up to xn part n. This is also balanced set 2, and this will continue up to n components. Now what does it mean? That if we have a set of 3 unbalanced phases, now we are sort of applying this Fortescue theorem to a 3-phase system. Fortescue theorem applied to 3-phase systems. Right? Now what does this mean? That here we have 3 unbalanced phases. Let's say I have phasor A as red, then I have phasor B as yellow, and I have phasor C as. Now here you can clearly see that this is an unbalanced phases. Now when we are applying Fortescue theorem to this means what? That this set of unbalanced phasors can be broken down into 3 sets of balanced phasors always. Since we had 3 unbalanced phasors here, so this means there will be first one, second one and third one. And the sum of these unbalanced phasors will actually give you the the sum of these balanced phasors will actually give you the original unbalanced. Now the first component among these is referred as the positive sequence. A yellow, B and blue. Now why it is called as the positive sequence? Because we know that phases are continuously rotating. It is referred as positive sequence because the direction of rotation is the same as the original sets of unbalanced phases. Only the direction, the magnitude will change definitely. The angular difference will here be exactly 120 degrees. Why? Because these are all balanced, 120, 120 and 120, right? These are referred as positive sequence components, right? Positive sequence components. Why they are referred as positive sequence components? Because the direction of rotation is the same. Now let's say I keep this point as my reference. This is my reference point and I am saying that these phasors are rotating either in clockwise or anti-clockwise. At the moment I am saying it's clockwise. Now when this phasor rotates, the first phase that comes to the reference point here is what? A. The first phase is A. After that we have B and after that we have C. Clear? Now if we look at this positive sequence, the first phase that comes here is again A, next one is B and C. This means its direction of rotation or phase sequence is the same as the original set of phasors, and that is why we call these as positive sequence components. Got it? The next set of phasors is called as the negative sequence components. Here, this one is also rotating clockwise, but here now the direction of rotation would be opposite, anti-clockwise. Red, yellow, these are all balanced, and blue. A, B the angle again is 120 degrees, right? 120, 120, and 120. Now again, looking at the reference point. Now the direction of rotation is different. As you can see, this is rotating anti-clockwise. So the first element, first phasor that comes is C here, then comes B, and then comes A. C, B, A, C, B, A. Now since our reference has got to be from A, so here the phase sequence is A, C, B, and you can see that it is opposite as compared to the original set of phasors, and that is why it is referred as negative sequence components. I hope it's clear. And the third set of phasors is called as zero sequence components. Why they are referred as zero sequence components? Because the angular difference between all the three phases is zero. Red, yellow, and blue. Here the angular difference you can see between all the phases A, B and C is 0. So what we have done, just to summarize it, for unbalanced fault analysis, we are dividing our system of three unbalanced phases into a sum of balanced phases. Now I am repeating this one. Positive sequence components are balanced among themselves. That means the A, B, C will have same magnitude among themselves, and positive sequence components are usually expressed with a subscript of 1, A1, B1 and C1. This means A1, B1 and C1 will have the same magnitude and their angular separation will be 120 degrees. Similarly, the negative sequence components A2, B2 and C2 will have the same magnitude among themselves and same angular separation of 120 degrees. A0, B0 and C0, the zero sequence components, will also have the same magnitude and angular separation also, which is 0. But it is not necessary that this A1 will be equal to A2 and A0. No. Within this own set, the phasors will be balanced, but not among the differences. Got it? Now what does this mean? That the phase A, right? Phase A in terms of phasor component is equals to what? A0 plus A1 plus A2. Phasor sum. Similarly, phase B is equals to B0 plus B1 plus B2, and phase C is equals to C0 plus C1 plus C2. Right? These are basically unbalanced phasors. These are positive sequence components. These are zero sequence components. These are positive sequence components, and these are negative sequence components. Right? So I hope it is clear. Alright, so now let's continue with the sequence networks. Once we have understood how we can apply the Fortescue theorem to a set of sequence networks, let's consider that we have three unbalanced voltages here: VA, VB and VC. Right? Let's consider the VC and this one. And we are at the moment assuming that the direction of rotation is anti-clockwise. So now, as per the Fortescue theorem, these voltages component, these three voltages can be broken down into three components which are balanced among themselves. So VA1, VB1 and VC1. Okay, and the direction of rotation again will be same, plus the negative sequence components, which will be VA2, VB2 and VC2, and its direction of rotation will be opposite. So we can say that it is the direction of rotation, and this will be V2 and this will be C, plus we have VA0, VB0 and VC. This is positive sequence components, this is negative sequence, and this is zero sequence. Right? Now one thing that we already know is that within a set, that is if we are considering these positive sequence components, the phasors are balanced and the angular difference here is 120 degrees between all the three phasors for positive and negative, and for 0 it is 0, and the magnitudes are also same. So what we can say is that first let's consider this. VA is equals to VA1 plus VA1 plus VA2. Same it as equation 1. Similarly, VB equals to, this is the original imbalance, this is equals to VB0 plus VB1 plus VC1, and is equals to VC0 plus VC1 plus VC2. Right? Now we can say that since the magnitudes are same, so VA1, if we consider VA1 equals to V1, then what will happen? VA1, if it is equals to V1, then we can see that there will be only 120 degrees difference here. So what we can say, VA1 is equals to V1, then VB1 will be equal to how much? You can see A1 to B1 is either minus 120 or plus 240, right? So V1 angle plus 240, anticlockwise is positive, and similarly VC1 is equals to VA1 VC1, sorry, this one is V1 angle plus 120 or minus 240 is also the same. Okay. Okay, so now let's say that VA2 is equals to V2. Then here you need to see, previously we were taking the anticlockwise angle as positive. Why? Because the direction of rotation was the same. So the phasors was rotating anticlockwise, so we were taking anticlockwise angle as positive and clockwise as negative. But in here, in negative sequence components, the direction of rotation has changed. So we will be taking clockwise angle as positive and anticlockwise angle as negative. So Now VB2 will be equals to, and VC2 will also be equals to V2 times VB2 is here, so either plus 120 or minus 240, and VC2 is V2 angle plus 240 or minus A2 and B2. From A2 to B2 we have anti-clockwise, clockwise, and it's the same as the original direction of rotation phases, so that is taken as positive. Right? And then for zero sequence, if we have let VA0 equals to V0, then VB0 will also be equals to V0, VC0 will also be equals to V0, because there is no angular separation here, and mind you, V0, V1 and V2 are phasors. Now what we are doing, let's say that this 120, 240 is creating a bit of complexity, so we are saying, okay, again let A is equals to 1 angle 120, right? We are assuming a vector A, which is a unit vector, magnitude 1, having a displacement of 120 degrees, right? This means that A square will be equals to 1 angle 240 or 1 angle minus 120, both are time, and A cube will be equals to 1 angle 0, right? And one more thing that we need to understand is that 1 plus A square, when you solve it by the help of calculators in complex numbers, this would yield 0, right? So now we can write the equations 1, 2 and 3. We can rewrite them. So equation 1 will be rewritten as VA1, which is what? V0 plus V1. So VA is equals V0 plus V1 plus V2, right? VB equals V0, this is VB, right? V0 plus A square V1. This 1 angle 240 is A square V1 plus this is A V2, right? And VC, this is equation, this was equation 2, and then we have 3 also. We can write VC as V0 plus V1 A, 1 angle 120 is A, V0 plus A V1 plus A square V2. And we can now simplify this in the matrix form. This will now become VA, VB, VC equals 1, 1, 1, 1 A square A, 1 A square, V0, V1 and V2, or we can generalize it by writing VABC, let's write red color, VABC equals A times of V012 or Vp, that is the phase voltages, is equals to A times of Vs, which is the sequence voltages. And always remember, A is called as sequence component transformation matrix. A is called as symmetrical component transformation matrix. A is symmetrical component transformation matrix. Right. So now we can write it as we can do the reverse also. Vp is equals to A times Vs, which means Vs will be equals to A inverse of Vp. Now Vs is equals to A inverse of Vp. And for matrix A, we already know what is A. A is equals to 1 1 1 1 A square A 1 A square. When we take its inverse by taking the determinant and then dividing it with transposes, A inverse will be equals to 1 over 3. Now this is easy, just swap the values of A and A square in the rows or in the columns. This is a symmetrical matrix. 1 1 1 1 A square and 1 A square A, where A is equals to, we already know, 1 angle 1. So now we can find out that if we have the symmetrical, if we want to find the symmetrical components from the phases, right, what we need to find here, V0, V1 and V2. So this would be equals to 1 over 3 A inverse, which is 1 1 1 1 A square 1 A square A, VA, VB and VC, right? So this is basically the process of finding out the voltages with respect to current. So now we know V0 will be equals to 1 over 3 VA plus VB plus VC. Mind you, VA, VB and VC are all phases. V1 is equals to 1 over 3 VA plus A times of VB plus A square times of VC, and V2 will be equals to 1 over 3 VA plus A square times of VB plus A times of VC, right? And similarly, if we want to find the currents, I0, zero sequence current, will be equals to 1 over 3 IA plus IB plus IC. I1 will be equals to 1 over 3 IA plus AVB plus A square BC, and I2 will be equals to 1 over 3, this is IB and IC. IA plus A square IB plus AIC. Now this is the process for finding out the sequence components with respect to the from the original phases, and if we want to find the original phases from the sequence components. Then we have this equation which we already derived previously, right? This one. So I hope it is clear. Okay, so now let's go through one or two numericals related to sequence component calculation. The first question is that we are given the symmetrical components. We are asked to find the currents based on the value of unbalanced phasors. So this is question 1 in fact. It says IA equals, given IA equals 1.6 angle 25 degrees amperes, IB equals 1 angle 180 degrees amperes, and IC equals 0.9 angle 132 degrees amperes. We need to find I0, I1 and I. That is, we are given the phase components and we are asked to find the sequence components. Right? So I0, we all know as per our discussion in this lecture earlier, is equals to 1 over 3 IA plus IB plus IC, and this will be equals to 0.45 angles 96.45 degrees. This is next. We need to find I1 equals 1 over 3 IA plus A times of IB plus A square times of IC, and when we solve it using A as 1 angle 120 degrees, this comes out as 0.94 angle minus 0.054 degrees. This is I1. And finally we have I2 equals 1 over 3 IA plus A square times of IB plus A times of IC equals 0.6. This will be 0.6 angle 22.3 degrees. This is I2. So how can we draw these now? Just I0 we know is the same. This is 0 degrees. 96.45 is the angle. Right? This is 90. This is 0. Right? So somewhere here, and all these three will be same. So this would be IA0, I B0 and I C. Then we have, alright, so coming towards the positive sequence, we can say I1 is 0.94 minus 0.05, so this is 0. This would be IA1, and we know that between IA1 and IB1, how much is the difference? It is 120 degrees in this, in clockwise direction, or minus 120 degrees if clockwise, and 240 degrees in anti-clockwise, right? So we have gone minus 120, means minus shows clockwise. This is IB1 and this will be somewhat IC1. Again this is 120 and 120. Same will be the case for a negative sequence. For negative sequence, we know angle is 22.3, so this would be IA1. Ideally, when we have IA2, we have phasors like this, right? So all will be displaced by this would be same in magnitude. IA2 is, and this would be IP2, and this would be IC. This dotted line shows the position if the angle was 0 over 20 and 40 respectively. This would be IL2 will be 0.6, angle 22.3 degrees. Yeah. 0.6 angle 22.3 degrees, and B2 and B3. Accordingly, this is 0.94 and minus 0.05 degrees. This is equals to 0.45 angle 96.45 degrees ampere. Now let's look at another example in which we need to do the opposite. Like we have the sequence components here, and we want to find the value of phasors, the unbalanced phasors, right? So what we need to do here is question number 2. It says that we are given the values as VA0 equals 0.6 angle 90 degrees volts. This can be in per unit as well, but here it is VA1 equals 1 angle minus 30 volts, and VA2 equals 0.8 angle 30 degrees. We need to find VA, VB and VC, right? As we discussed earlier in this lecture, we can find these values as VA equals VA0 plus VA1 plus VA2. So this will be equals to, when we add them, this will give us 1.63 angle 17.7 degrees. Similarly, VB equals VA0 plus A square V1 plus A times VA2, and when we solve it, it will give me 1.63 angle 162 degrees volts, and VC will be equals to VA0 plus A times VA1 plus A square times VA2, and this will give me 0.8 angle 90 degrees. Right? One thing you will see that it is a further proof that when we add these symmetrical components, these were all symmetrical. Zero sequence within them balanced, positive sequence within them balanced, negative sequence within them balanced. But when adding the vector, taking the vector sum, phasor sum, these components are unbalanced. Magnitude is 1.63, 1.63, 0.8. Angular separation is also not the same. When we draw it, it would be like VA is 17.7, so this would be VA VB is 162.2, so it would be somewhere here. This is 17.7, this is 162.2, and VC is 90 degrees. And now you can see that these are unbalanced components, right?